Hello everyone, welcome to today's presentation. I'm excited to have you all here. Today we will be exploring the fundamental concepts of units in measurement. The main focus will be on the definition of fundamental units and derived units. This is lesson number 2, or he pat, inus, he kremak, inus 2 in our series. Over the next few slides, we'll delve into what these units are, why they matter, and how they are used in various fields. So, let's get started and make this session engaging and informative. He abenos, he humenos, he puntavlocanenos, he keanos, he isenos, he kundenos, he meanos, he heanos, he pahaleanos, he patenos, he meanos, he humneanos, he botacanos, he jugatanos, he kaenos, he udyanos, he keanos. He gismeanos, he mapanenos, he odanos, he matakoinos, he kienos, he mahetvaporaenos, he bhumakaenos, he tianos, he yahenos, he samajnaenos, he jatudianos, he haenos, he kilenos, he humeanos, he upneanos, he chatoanos, he odanos, he joanos, he bhienos, he mapteanos, he haenos. He veanos, he subhienos, he mapanenos, he kienos, he ptuktianos, he odanos, he akaioinos, he pudanos, he nidpudanos, he kutteanos, he haenos. He agenos, he kaenos, he mukianos, he pokasenos, he yahenos, he haenos, he kilenos, he humenos, he mulenos, he dashioinos, he kianos, he pudibhashainos, he koinos, he sumcheanos, he yaenos, he mulenos, he dashianos, he mapanenos, he kienos, he nivenos, he haenos, he jinseanos, he humenos, he unyanos, he mapoinos, he koinos, he pudibhashatanos, he kutteanos, he haenos, he anos. He humenos, he unanos, he vyutpunnaenos, he dashioinos, he koinos, he bhienos, he dekegeanos, he joaenos, he mulenos, he dashioinos, he seanos, he buntianos, he haenos, he odanos, he hamateanos, he dojamertaenos, he keanos, he jivanenos, he meanos, he bohutanos, he kamenos, he atianos, he haenos. He yahenos, he samajnaenos, he bohutanos, he jatudianos, he haenos, he keanos, he innenos, he mulenos, he dashioinos, he odanos, he vyutpunnaenos, he dashioinos, he kaenos, he gyanenos, he hamateanos, he vigyanenos, he odanos, he technikenos, he keanos, he vakasenos, he meanos, he adharenos, he haenos, he iseanos, he humenos, hindi he nainos, he kavalaenos, he mapanenos, he keanos. He sahienos, he tadikeanos, he janaenos, he sakteanos, he haenos, he bulkianos, he unkaenos, he opyagenos, he bhienos, he behatarenos, he tadikeanos, he seanos, he kudanos, he sakteanos, he haenos. He taenos, he istaenos, he pudaenos, he patenos, he kaenos, he udasianos, he haenos, he kilenos, he humenos, he indenos, he buniadianos, he avtadnaenos, he koenos, he sumcheanos. He takianos, he ageanos, he humenos, he inkaenos, he sahienos, he odanos, he ptapavianos, he estemalenos, he kudanos, he sakeanos, he yahenos, he hamatianos, he udyanenos, he yataenos, he kaenos, he akenos, he mahetvaporaenos, he kudamenos, he haenos. He joaenos, he humeanos, he veganikenos, he sachenos, he odanos, he mapanenos, he keanos, he sahienos, he tadikeanos, he upnaneanos, he meanos, he mudidanos, he kategaenos. He yahenos, he slideanos, he hamateanos, he intertashtianos, he matakenos, he pudtianos, he keanos, he mulenos, he matakoenos, he koenos, he samchaneanos, he kaenos, he pliasenos, he haenos, he yahaenos, he parenos, he humenos, he dekenos, he sakteanos, he haenos, he kilenos, he mulenos, he botakenos, he dashioinos, he koenos, he mapneanos, he keanos, he liganos, he kisenos. He ptakataenos, he keanos, he matakenos, he odanos, he ptatikenos, he opyagenos, he kirianos, he jateanos, he haenos, he taenos, he subseanos, he pahaleanos, he davyamanenos, he keanos, he liraenos, he kalogdamenos, he kaenos, he ptayagenos, he hotaenos, he haenos. He jiskaenos, he ptatikenos kg, he haenos, he yahenos, he bohutaenos, he hirenos, he mahetvaporaenos, he haenos. He yahenos, he vastuenos, he kaenos, he vajanenos, he dershaneanos, he kaenos, he adharenos, he haenos. He iskeanos, he badaenos, he lumbianos, he keanos, he liganos, he metadenos, he kaenos, he opyagenos, he kiaenos, jatainos, heinos, orenos, oskainos, ptatikenos, heinos, iahenos, mapanenos, hamatenos, tajamertainos, kanos, jivanenos, maenos, bhidenos, bohutenos, kamenos, atainos, heinos. Jaseanos, kirinos, dudienos, mapneanos, maenos. Samaenos, koinos, mapneanos, kanos, litenos, secundenos, kainos, priogenos, kiainos, jatainos, heinos, juskainos, ptatikenos, heinos, samaenos, kainos, iahenos, mapenos, hamateanos, subhienos, vegianicanos, priogoinos, orenos, tajamertainos, kienos, gutavidioinos, kainos, adharenos, heinos. Tapmanenos, kaenos, lirenos, kelvanenos, kaenos, ptiogenos, hotaenos, heinos, orenos, oskainos, ptatikenos, heinos, iahenos, tapmanenos, kaenos, akenos, manikenos, heinos. Jainos, bohutenos, hienos, viapakenos, dupenos, seanos, vegianicanos, ptiogoenos, maenos, estemalenos, kainos, jataenos, heinos. Vidutenos, tataenos, kaenos, lirenos, ampiarenos, kaenos, piogenos, kainos, jataenos, heinos, orenos, eskainos, ptatikenos, heinos, iahenos, vidutenos, ptavahenos, kienos, tivdatainos, koinos, dershataenos, heinos. Ptadipanenos, tivdatainos. Yanienos, ptakashenos, kienos, matainos, kanos, lirenos, kerelaenos, priogenos, hotainos, heinos, orenos, eskainos, ptatikenos, seed, heinos, iahenos, ptakashenos, kanos, stotenos, kienos, shaktienos, koinos, mapneanos, kanos, lirenos, jatudienos, heinos. Padatenos, kienos, mataenos, koinos, mapneanos, kanos, lirenos, malenos, kainos, priogenos, kiainos, jataenos, heinos, juskainos, ptatikenos, mal heinos, iahenos, dasainikenos, abhictiawenos, orenos, padatoinos, kienos, sunkiaenos, koinos, sumajneanos, maenos, mudadenos, kutainos, heinos. Pidaenos, chalivagenenos, dadianenos, kainos, priogenos, hotainos, heinos, jainos, akenos, karenos, mapneanos, kaenos, putakenos, matakenos, heinos, orenos, eskainos, ptatikenos, rad, heinos, iahenos, karenos, mapenos, bohutenos, hienos, sukshmaenos, orenos, sachikenos, hotainos, heinos. Untenos, maenos, stadadianenos, kainos, priogenos, hotainos, heinos, jainos, tasenos, karenos, mapenos, heinos, orenos, eskainos, ptatikenos, asar, heinos, iahenos, tinenos, ayamianos, karenos, mapneanos, kanos, lirenos, estemalenos, kainos, jatainos, heinos. Tainos, inanos, subhienos, mulenos, matakaenos, kaenos, estemalenos, pudienos, duniaenos, maenos, mankictatenos, mapenos, kaenos, lirenos, kaiaenos, jataenos, heinos. Jainos, vegianicanos, vidhioinos, orenos, technicianos, ptugdianos, kainos, adharenos, buntainos, heinos, iahenos, sumajnainos, jatudianos, heinos, kirinos, ianos, matakenos, hamateanos, jivanenos, kaenos, hutenos, kshetaenos, maenos, bhumakaenos, nibhateanos, heinos. Now, let's take a closer look at the fundamental units of the International System of Units, or SI for short. These are the building blocks that help us measure the world accurately and consistently. Starting with mass, which is essentially how much matter is in an object, the SI unit is the kilogram, abbreviated as kg. This is perhaps one of the most well-known units, especially in everyday life. Next up is length, which measures how long or wide something is. The SI unit here is the meter, symbolized by an m. Think of it as the standard measure for distance. Moving on, time is fundamental as well. It's measured in seconds, abbreviated S. Everything from scientific experiments to daily routines relies on precise time measurement. Temperature is another key quantity, and we measure it in Kelvin, symbolized as K. Unlike Celsius or Fahrenheit, Kelvin starts at absolute zero, which is the coldest possible temperature. Electric current, which is the flow of electric charge, is measured in amperes, or amps. With the symbol A, this unit is critical in electrical engineering and power systems. Then we have the intensity of illumination, measured in candelas, abbreviated as seed. It helps quantify how bright a light source appears to the human eye. The amount of substance, or the number of particles in a sample, is measured in moles, symbolized as mol. This unit is fundamental in chemistry for counting molecules and atoms. Now, moving into the realm of angles, we have the planar angle, measured in radians, rad. This is a bit different from linear measurements, as it describes the size of an angle in a circle. Similarly, for solid angles, which describe three-dimensional angular spans, the unit is the steradian, SR. Think of it as the three-dimensional equivalent of radians. And a quick note, these last two, radians and steradians, are what we call complementary units. They're essential for describing angles in both 2 and 3 dimensions, connecting nicely to our overall theme of understanding measurement in the universe. So, these units form the core of how we quantify everything from the tiniest particles to vast celestial objects, providing a universal language for science and engineering. Now, let's talk about what a meter actually is. A meter is a fundamental unit of length that helps us measure distances. But how do we define it precisely? Well, 1 meter is the distance traveled by light in vacuum during the time it takes for approximately 1.65 million waves of a specific orange-red light emitted by the krypton 86 atom to pass by. That's quite a precise and scientific way to define length, isn't it? Instead of relying on physical objects, we're using the behavior of light, which is constant and universal. To put it into perspective, we often convert meters into larger and smaller units for convenience. For example, 1 kilometer equals 1,000 meters. This makes sense because a kilometer is just a bigger unit, used for measuring longer distances like roads or cities. Similarly, when we go smaller, 1 centimeter is 1/100th of a meter, and a millimeter is 1/1000 of a meter. These smaller units are useful for more detailed measurements, like in engineering or medicine. And if we go even smaller, there's the micrometer, which is 1/1,000,000th of a meter. This is often used in science and technology fields, especially when dealing with tiny structures, like cells or microchips. So, understanding these units and their relationships helps us measure everything from vast distances to microscopic details, all grounded in the very precise definition of a meter itself. It highlights how science gives us a universal way to measure the world around us, no matter how big or small. Now, let's take a closer look at some important subunits of the meter, which are essential for understanding measurements at very small scales. First, we have the nanometer, which is 1/1000,000th of a meter. In scientific notation, we write it as 10 to the power of -9 meters, and in Hindi, we say 10 to the -9 meters as well. Next, there's the angstrom, which is even smaller, just 10 to the -10 meters. This unit is commonly used in atomic and molecular scales, making it very important in fields like chemistry and physics. Then we come to Fermi, which is 10 to the -15 meters. This unit is named after the physicist Enrico Fermi and is particularly useful when talking about nuclear and particle physics. Understanding these subunits helps us grasp the incredibly tiny scales involved in modern science, especially when we're dealing with atoms, molecules, or particles. They allow us to measure and describe phenomena that are far beyond the reach of everyday measurements, connecting directly to the overall theme of precision and scale in measurement science. Let's take a closer look at this diagram for 1 meter. What we're seeing here is the concept of a single wave spanning a 1 meter length. Now, interestingly, the number of waves that can fit into this 1 meter is approximately 1,650,763.73. That might sound like a strange number, but it highlights just how incredibly dense these waves are at this scale. And right here, we've got an example of a Kr86 atom. This atom is shown emitting waves, which is a key point because it illustrates how atoms themselves are sources of these waves. These emitted waves are fundamental to understanding how energy and information travel at the atomic and subatomic levels. Connecting this to our overall theme, what we're emphasizing is the relationship between atomic structures and wave phenomena. The fact that such a large number of waves can fit into just 1 meter underscores the incredibly fine wavelength scale we're dealing with in quantum physics. So this diagram isn't just about numbers. It's about visualizing how tiny, yet densely packed, these waves are at the atomic scale, which is essential for understanding the behavior of particles and energy in our universe. Now, let's take a closer look at what a kilogram truly represents. First, we define it in terms of a physical object. 1 kilogram is equivalent to the mass of a specific platinum-iridium alloy cylinder kept at the International Bureau of Weights and Measures in Paris. This cylinder has a height and diameter of 3.9 centimeters. So, when we say 1 kilogram, we're referencing a tangible object with a known, fixed mass. Next, we connect this to something more familiar, water. At 4 degrees Celsius, which is the temperature at which water is most dense, 1 liter of water has a mass of exactly 1 kilogram. This gives us an everyday context. If you fill a 1-liter bottle with water at this temperature, you have 1 kilogram of water. Now, moving to the atomic level, 1 kilogram can also be thought of as the mass of approximately 5 times 10 to the 25th atoms of carbon-12. This highlights how the kilogram links the macroscopic world to the microscopic world, showing us the vast number of atoms that make up a seemingly simple unit of mass. Let's also briefly touch on the subunits of the kilogram, as understanding these helps us grasp different scales of measurement. 1 kilogram equals 1,000 grams, which is straightforward. Smaller units include the milligram, which is 1,000th of a gram, so 10 to the minus 3 grams. On the larger scale, we have the quintal, which is 102 kilograms, and the ton, which is 1,000 kilograms. By understanding these different units and their relationships, we see how the kilogram serves as a fundamental building block for measuring mass across various contexts, whether we're talking about tiny particles or massive loads. This interconnectedness emphasizes the importance of the kilogram as a standard in science and everyday life, aligning with our overall theme of measurement and standardization. Now, let's explore what we mean by 1 kilogram and how it's actually defined. The most precise standard we have is the platinum-iridium cylinder kept in Paris at the International Bureau of Weights and Measures. This cylinder has a height and diameter of about 3.9 centimeters, and it serves as the official reference for the kilogram. It's fascinating to think that this tiny object essentially defines the mass we use every day. But here's an interesting point. 1 kilogram isn't just a random number. It corresponds exactly to the mass of 1 liter of water at 4 degrees Celsius, which is the temperature at which water reaches its maximum density. This connection ties the abstract concept of mass to something tangible, water, making it easier to understand and relate to. And on another level, a kilogram also relates to atoms. Specifically, it's the mass of approximately 5 times 10 to the 25th atoms of carbon-12. That's a staggering number, but it helps us understand just how tiny individual atoms are and how a large quantity of them adds up to something as familiar as a kilogram. So, throughout our presentation, keep in mind how these different perspectives, physical objects, liquids, and atoms, are all interconnected in defining what a kilogram truly is. It's a perfect example of how measurements blend the tangible with the microscopic, linking everyday experience with the fundamental building blocks of matter. He taenos, he yahaenos, he humenos, he batenos, he karenos, he dahenos, he herenos, he ekenos, he secundenos, he kienos, he yanienos, he osenos, he sameanos, he kienos, he joinos, he ekenos, he padmaroenos, he gartienos, he meanos, he mapienos, he jatienos, he herenos, he casenos, he batenos, he yahenos, he herenos, he kivenos, he ekenos, he secundenos, he vahenos, he sameanos, he herenos, he gismeanos, He CGManos 133, he Padmadoenos 9,192,631,770, he Badanos, he Upnianos, he Tatunganos, he Companenos, he Cutanos, he Haenos, he Asianos, he Parenos, he Humeanos, he Upnianos, he Sumeanos, he Kianos, he Mapanos, he Koinos, he Padibhashatanos, he Kudnainos, he Hotainos, he Haenos, he Ubanos, he Chautianos, he Uvtianos, he Kianos, he Batanos, he Cudanos, he Tauanos, 1 he Millisecundanos, he Yanianos 10 3 he Secundanos, he Audanos, he Mictosecundanos, he Yanianos 10 6 he Secundanos, he Yanos, he Donoinos, he Pianos, he Bahutanos, he Chautianos, he Sumeanos, he Kanos, he Entadalanos, he Haenos, he Jinkainos, he Estemalanos, he Amtadanos, he Pudanos, he Electonicanos, he Upakutnaenos, he Audanos, he Nativudkanos, he Maenos, he Hotainos, he Haenos, he Iskaenos, he Badanos, he Haenos, he Nanosecundanos, he Joinos 10 9 he Secundanos, he Canos, he Batabadanos, he Haenos, he Yanianos, he Akanos, he Udabuanos, he Secundanos, he Yahanos, he Sumeanos, he Mapanos, he Bahutanos, he Hianos, he Sukshmanos, he Hotianos, he Haenos, he Kasakadanos, he Adhunikanos, he Ptodyogikianos, he Maenos, he Jasanos, he Kilanos, he Potonanos, he Kaianos, he Ptabuntanos, he Yavenos, he Behatadanos, he Sanchadanos, he Technicanos, he Kaenos, he Livanos, he Odanos, he Untanos, he Maenos, he Picosecundanos, he Yanianos 10 12 he Secundanos, he Joinos, he Kilanos, he Akanos, he Tilianvianos, he Secundanos, he Canos, he Batabadanos, he Haenos, he Yahanos, he Subsayanos, he Chautianos, he Mapanos, he Haenos, he Jisayanos, he Humanos, he Ubhianos, he Pianos, he Padibhashatanos, he Cudanos, he Suktayanos, he Haenos, he Kasakadanos, he Quatamanos, he Pajixanos, he Yainos, he Atiadhunikanos, he Veganikanos, he Ptayagoanos, he Maeanos, he Tauanos, he Inanos, he Subhianos, he Chautanos, he Sumeanos, he Kaenos, he Manakanos, he Humeanos, he Bahutanos, he Hidanos, he Sachiktanos, he Sayanos, he Sumeanos, he Koinos, he Mapneanos, he Maeanos, he Mudadanos, he Kutayanos, he Haenos, he Audanos, he Yahanos, he Humeanos, he Hamateanos, he Pudayanos, he Technicianos, he Audanos, he Veganikanos, he Kamkajanos, he Kianos, he Nivanos, he Pianos, he Ptadananos, he Kutayanos, he Haenos, he Yanos, he Subhianos, he Avtadnayanos, he Humeanos, he Decatianos, he Haenos, he Kiranos, he Sumeanos, he Kitnianos, he Sukshmanos, he Stutanos, he Pudanos, he Pianos, he Mapaenos, he Javinos, he Suktainos, he Haenos, he Audanos, he Yahanos, he Hamatianos, he Dunianos, he Kanos, he Batikanos, he Pahaloinos, he Koinos, he Samajnaenos, he Maeanos, he Kitnainos, he Mahitvaporainos, he Haenos. Let's talk about what an ampere actually is. Imagine you have 2 very long, straight wires placed parallel to each other in a vacuum, so there's no air or other particles around. These wires are infinitely long, meaning they extend without end in both directions. Now, if we send an electric current through each of these wires, something interesting happens. The currents in the wires interact with each other, creating a force. Specifically, if the current is exactly 1 ampere in each wire, they will exert a particular force on each other. This force per meter of wire length is exactly 2 times 10 to the minus 7 newtons. To put that in perspective, it's a very tiny force, but it's significant enough to define what 1 ampere is. So 1 ampere is the amount of current that, when flowing through 2 such parallel wires, produces this precise force of 2 times 10 to the minus 7 newtons between them. This definition helps us quantify electric current in a very precise way, linking the abstract concept of current to a measurable physical force. It's a fundamental concept that connects electromagnetism directly to the measurement of electricity itself. Let's take a closer look at this diagram for ampere. Imagine 2 infinitely long wires, each carrying a current of 1 ampere. Because the wires are infinitely long, we can consider the magnetic effects to be uniform along their length, which simplifies our analysis. The distance between these 2 wires is exactly 1 meter, and importantly, the wires are positioned so that their midpoints are 1 meter apart as well. Now, when these currents flow through the wires, they exert a force on each other. In this case, the force between them is 2 times 10 to the power minus 7 newtons. This tiny force might seem small, but it actually illustrates a fundamental principle, that currents in wires produce magnetic fields which then interact, creating forces. This example helps us understand how magnetic forces between currents depend on factors like current strength, the distance between wires, and the length over which these interactions occur. It's a key piece in understanding electromagnetic interactions, and it ties directly into how we can control and utilize magnetic forces in practical applications. Now let's look at what a candela really represents. Essentially, it's a measure of the intensity of light emitted in a specific direction. To be precise, one candela is defined as the luminous intensity perpendicular to a black body's surface when the area of that surface is just 1 over 600,000 square meters. Think of it this way. We're talking about a tiny, tiny area, so small that its area is just a fraction of a square millimeter, and measuring the light emitted straight out from it. Now, this black body, which is a theoretical ideal emitter, is also at a specific pressure, 101, 325 newtons per square meter, which is actually the standard atmospheric pressure we experience at sea level. And then there's the temperature involved. The temperature at which this black body radiates with that specified intensity is equal to the melting point of platinum. That's quite fascinating because it links the concept of luminous intensity to physical properties like pressure and temperature of materials, making the definition very precise and scientifically grounded. So, when we talk about a candela in this way, we're connecting something as seemingly simple as light to these fundamental physical conditions, which helps us understand how luminous intensity is standardized across different environments and applications. This concept ties back into the overall theme of measurement and standardization in physics and engineering, ensuring that when we specify a candle power, we're all speaking the same language about light's intensity. Now, let's take a closer look at this diagram related to candela, which is a fundamental unit of luminous intensity. As you can see here, we have a black body, which is essentially an idealized object that absorbs all radiation falling on it. From this black body, some radiations are emitted in various directions, but what's important for understanding candela is the radiation that is emitted perpendicularly, or straight out from the surface. This radiation passes through a given surface, which helps us visualize how luminous intensity is measured in a specific direction. The concept here is that the black body acts as a source of light, and the amount of light passing through that surface in a particular direction is what defines the luminous intensity in that direction. This diagram highlights the importance of directionality in light measurement. When we talk about candela, we're really focusing on the intensity of light in a specific, perpendicular direction. So, understanding this emission and how it passes through surfaces helps us grasp how luminous intensity is quantified and standardized. Overall, this visual connects to our broader discussion on brightness, light measurement, and how we define units like the candela, which ultimately helps us understand and compare luminous outputs from different sources. Now let's talk about the Kelvin scale and what makes it so fundamental in thermodynamics. One key point is that a single Kelvin, or 1 unit of temperature on this scale, is defined based on the properties of water. Specifically, it's 1/100th, or 1/100, of the temperature difference between water's boiling point at normal atmospheric pressure and the melting point of ice. In other words, if you take the difference between these two temperatures, dividing it into 100 equal parts gives you 1 Kelvin. This approach ties the Kelvin scale directly to a physical property of water, making it a practical and universal standard. Now, the second important point relates to the triple point of water, which occurs at 273.16 Kelvin. This is the unique temperature and pressure condition where water can coexist as a solid, liquid, and vapor simultaneously. 1 Kelvin, in this context, is defined as 1/273.16 part of the thermodynamic temperature at this triple point. So, to sum up, the Kelvin scale is anchored in real physical phenomena, both the temperature difference between freezing and boiling points and the triple point of water. This makes it a very precise and universal measure of temperature, essential for scientific work across the globe. Connecting these points helps us understand why the Kelvin scale is so fundamental in thermodynamics, ensuring consistency and accuracy in temperature measurement everywhere. Let's talk about what a mole really is. A mole is a way to measure a specific amount of a substance. Now, when we say 1 mole of a substance, we're talking about a quantity that contains as many fundamental particles, like atoms or molecules, as there are in 0.016 kilograms of oxygen, which is essentially 8O16. This means that in that small amount of oxygen, the number of oxygen atoms is exactly the same as the number of particles in 1 mole of any other substance. Similarly, 1 mole of a substance also corresponds to a mass where the number of its fundamental components, say, atoms, matches the number of carbon atoms in 0.012 kilograms of carbon, specifically 6C12. So, whether we're measuring oxygen or carbon, the idea is that 1 mole represents a fixed, countable number of particles, just scaled to the mass of that specific element. This concept is really powerful because it allows us to relate the microscopic world, those atoms and molecules, to the macroscopic world we can measure easily. When we say 1 mole, we're talking about a very specific, consistent count of particles, making it easier to do calculations in chemistry. It bridges the tiny atomic scale with the larger quantities we work with in labs and industry. Now, let's talk about the complementary unit of measurement for angles, which is the radian. A radian is a way to measure angles based on the geometry of a circle. Specifically, 1 radian is defined as the angle subtended at the center of a circle by an arc whose length is equal to the radius of the circle. To put it simply, if you imagine an arc on the circle that's exactly the same length as the radius, the angle created at the center by that arc is 1 radian. This concept is very important because it connects the length of an arc directly to the angle it subtends, making calculations much more straightforward in many cases. The key formula here is that the angle in radians, theta, is equal to the length of the arc, s divided by the radius, r, so theta equals s over r. Understanding this helps us see why radians are such a natural way to measure angles, especially in higher mathematics and physics, because they relate the linear and angular measurements directly. So, when we talk about radians, we're really talking about a way to measure angles based on the intrinsic properties of the circle itself. This is fundamental to understanding more advanced concepts in trigonometry, calculus, and beyond. Let's talk about the concept of radians, which is fundamental in understanding angles in a circle. When we say s equals the length of an arc, r is the radius of the circle, and theta is the angle subtended by that arc at the center. These are the key components. Now, if the length of the arc s is equal to the radius r itself, then from our basic arc length formula, we find that theta equals 1 radian. This is a very important point because it helps us understand what a radian actually measures. Essentially, 1 radian is the angle subtended when the arc length is exactly equal to the radius. Also, a quick note to keep in mind. 1 degree is equal to pi divided by 180 radians. So, whenever you're converting between degrees and radians, remember this conversion factor. Understanding this relationship is crucial because radians are often more natural for mathematical calculations involving circles and angles, especially in higher mathematics and physics. And this concept really ties into the overall theme of how we measure and understand angles in a more precise way than just degrees. Now, let's take a closer look at this diagram, which is all about understanding what a radian is. Here, we see an arc on a circle, and this arc has a length labeled as s. The key idea here is that the angle theta, which is subtended at the center of the circle by this arc, is directly related to the length of the arc itself. Specifically, the relationship is theta equals s divided by r, where r is the radius of the circle. This means, if I have an arc length of s, and I know the radius, I can find the angle in radians simply by dividing s by r now. An interesting point here is when the arc length s equals the radius r in that case. If I substitute s as r into the formula, I get theta equals r divided by r, which simplifies to 1. So, When the arc length equals the radius, the angle theta is exactly 1 radian. This concept is fundamental because it connects the physical length of an arc with the angular measure at the center, giving us a precise way to measure angles in radians. And this idea of radians makes calculations much more straightforward in trigonometry and calculus, especially when dealing with circular motion or periodic functions. So, understanding this relationship helps us see how angles and lengths are intertwined in the geometry of circles. Now, let's dive into the concept of a steradian. A steradian is a measure of solid angle, which might sound a bit abstract at first, but it's quite fascinating. Essentially, a steradian is defined as the angle that, when it is projected from the center of a sphere, subtends a specific area on the surface of that sphere. The key point here is that this particular area on the sphere's surface is equal to the square of the sphere's radius. To put it simply, if you imagine a sphere with a certain radius, then the area that corresponds to a steradian is exactly equal to the radius squared. This relationship helps us understand how we measure angles in 3 dimensions, not just in flat, 2-dimensional space. When we say 1 steradian, we're talking about that specific angle which encloses an area equal to the radius squared at the center of the sphere. Understanding this concept is crucial because it ties together the geometry of the sphere with the way we measure angles in 3 dimensions. It's a fundamental idea in fields like astronomy, physics, and engineering, where understanding the spread of light, radiation, or other phenomena over a spherical surface is essential. So, in essence, a steradian provides us with a standardized way to quantify how much of the sphere's surface is covered by a particular angle. It's a powerful tool that helps us analyze and describe spatial relationships in 3 dimensions more precisely. Hi abenos, hi hamenos, hi yahainos, hi steradianenos, hi kaenos, hi ekenos, hi chitaenos, hi dekenos, hi dahenos, hi haenos, hi yahenos, hi ekenos, hi bohotenos, hi hienos, hi mahetvaporenos, hi avtatnaenos, hi haenos, hi joinos, hi hameanos, hi galoenos, hi keanos, hi sandadpenos, hi meanos, hi samajnianos, hi hotienos, hi haenos, hi taenos, hi chaliaenos, hi isaenos, hi subtletaenos, hi seanos, hi samajteanos, hi haenos, hi hamenos, hi janteanos, hi haenos, hi kirenos, hi jubenos, hi hamenos, hi galenos, hi keanos, hi kedanos, hi parenos, hi koienos, hi bienos, hi karenos, hi banateanos, hi herenos, hi taenos, hi vahenos, hi karenos, hi kienos, hi satahenos, hi keanos, hi kshetapolanos, hi seanos, hi sambuntetenos, hi hotaenos, hi haenos, hi kasenos, hi batenos, hi yahenos, hi herenos, hi kirenos, hi yahenos, hi karenos, hi yanienos, hi kirenos, hi untatetenos, hi karenos, hi sidheanos, hi tadenos, hi padenos, hi galenos, hi kienos, hi satahenos, hi keanos, hi kshetapolanos, hi adenos, hi uskienos, hi seanos, hi jorhaenos, hi hotaenos, hi herenos, hi hamenos, hi istenos, hi batenos, hi koenos, hi istenos, hi tadahenos, hi seanos, hi bienos, hi kahenos, hi sakteanos, hi herenos, hi kirenos, hi galenos, hi keanos, hi kedanos, hi parenos, hi joinos, hi karenos, hi buntaenos, hi herenos, hi oseanos, hi hamenos, hi isenos, hi pormaleanos, hi seanos, hi mapenos, hi sakteanos, hi herenos. Omega hi betabit enos, hi herenos a divided by r hi kaenos, hi vadgenos, hi yahaenos, omega hi yanienos, hi kirenos, hi vahenos, hi karenos, a hi herenos, hi galenos, hi kienos, hi satahenos, hi kaenos, hi kshetapolanos, hi adenos r hi herenos, hi galenos, hi kienos, hi tigiaenos, hi tarenos, hi mukiaenos, hi batenos, hi yahenos, hi herenos, hi kirenos, hi yedianos, hi hamenos, hi pataenos, hi herenos, hi kirenos, hi kienos, hi satahenos, hi kaenos, hi kshetapolanos, hi kitnaenos, hi herenos, hi adenos, hi uskienos, hi kiaenos, hi herenos, hi taenos, hi hamenos, hi asanienos, hi seanos, hi osenos, hi karenos, hi koenos, hi mapenos, hi sakteanos, hi herenos, hi yahenos, hi pormalaenos, hi bohotenos, hi hidenos, hi subtleanos, hi herenos, hi adenos, hi yahenos, hi hamenos, hi galoenos, hi keanos, hi sandadpenos, hi meanos, hi bohotenos, hi satienos, hi ganawenos, hi meanos, hi mudadenos, hi kutaenos, hi herenos, hi istenos, hi tadahenos, hi yahenos, hi avtatnaenos, hi hamenos, hi galoenos, hi keanos, he vibhinnarenos, he pahaloenos, he koenos, he samajneanos, he maenos, he sahayakanos, he hodienos, he herenos, he orenos, he yahenos, he pureanos, he sedhetikenos, he tacheanos, he kaenos, he akenos, he mahitvaporaenos, he hissaenos, he herenos, he taenos. He uglyanos, he badanos, he jubanos, he apanos, he goloanos, he kaenos, he sandudpanos, he maenos, he kaenos, he yaenos, he kshetapulanos, he kianos, he batanos, he kadegaenos, he taenos, he isanos, he pormalaenos, he koenos, he jaturanos, he yadanos, he takiegaenos. Now let's move on to slide 22, where we look at the diagram for a steradian. As you can see, the diagram helps us visualize this concept more clearly. When we talk about a steradian, we're essentially describing a measure of solid angle in three-dimensional space. The key point here is the relationship between the area A on a sphere and the radius r if this area A equals r squared, which is r times r. Then we can directly relate this to the solid angle omega. From the earlier equation, equation 1, we find that when it equals r squared, the solid angle omega simplifies to 1 steradian. This is a crucial point because it gives us a clear, specific value of the solid angle in this particular case. So, in essence, this slide reinforces how the size of the area on the sphere and the radius are connected, and how that connection helps us determine the solid angle in steradians. This understanding is fundamental as we analyze light, radiation, or any phenomena involving solid angles in space. Now, let's move on to slide 23, where we focus on derived physical quantities. In physics, many quantities we deal with are not fundamental, but are derived from these basic quantities. For example, quantities like speed, acceleration, or force are all derived. They help us describe and understand physical phenomena more comprehensively. On this slide, you'll see a list of some commonly used derived quantities along with their units. It's important to remember that understanding these quantities and their units is essential for precise measurements and calculations in physics. Recognizing how these quantities relate to the fundamental ones ties into the overall theme of understanding the physical universe through measurement and analysis. So, getting familiar with these derived quantities and their units forms a key part of building a solid foundation in physics. Now let's move on to slide 24, which focuses on derived physical quantities, or he vyutpanna-enos, he bhautikanos, he dashiyanos. These are quantities that we derive from the basic or fundamental quantities in physics. Essentially, they help us understand more complex phenomena by combining basic measurements. For example, the first one is he kshetapul-enos, or area. It's measured in square meters, symbolized as m2. Think of it as the extent of a surface in 2 dimensions. Next, we have he ayaton-enos, or volume, measured in cubic meters, m3. This tells us how much space a 3-dimensional object occupies. Then there's he kanut-enos, or density, which is mass per unit volume, specifically in kilogram per cubic meter, kg/m3. Density helps us understand how tightly packed the material particles are. Moving on to motion-related quantities, we have he tal-enos, he ya-enos, he weg-enos, which is speed or velocity. It's measured in meters per second. ms speed tells us how fast something moves, while velocity also considers the direction. Following that is he twata-enos, or acceleration, measured in meters per second squared, ms2. It indicates how quickly an object's velocity changes over time. Similarly, angular acceleration, or he kani-enos, he twata-enos, is measured in radians per second squared, rad-s2. This describes how fast the rotational speed of an object changes. Next, we have he tatung-enos, he sankhya-enos, or wave number, which is given in inverse meters, m1. It relates to the number of wave cycles per unit distance, important in wave physics. Then there's he data-enos, he kanut-enos, or current density, measured in amperes per square meter, m2. This describes how electric current is distributed across a surface. Similarly, he umbaki-enos, Heat tivtatinus, or magnetic intensity, is in amperes per meter, AM1, indicating the strength of the magnetic field. We also have heat inus, heat tivtatinus, or intensity of illumination, measured in candelas per square meter, CDM2. This quantifies how bright a surface appears. Finally, heat inus, or momentum, is measured in kilogram meters per second, kgm1. It reflects the quantity of motion an object possesses. Throughout this list, you'll notice that each derived quantity combines fundamental units to give us a deeper, more specific understanding of physical phenomena. Recognizing these helps us connect basic measurements to real-world applications. Now, let's move on to the final slide, which covers some of the derived physical quantities. These quantities are essential because they help us understand and calculate various physical phenomena more effectively. First, we have the moment of inertia, which is a measure of an object's resistance to rotational motion. It's expressed in kilograms per meter squared, and the symbol we use is kg per meter squared. Think of it as the rotational equivalent of mass in linear motion. Next is the radius of gyration. This represents a distance from the axis of rotation at which the entire mass of the body could be concentrated without changing its moment of inertia. It is measured in meters with the symbol m. Moving on, the flow rate is the volume of fluid passing through a point per second, measured in cubic meters per second, or m3s. It's a key concept in fluid mechanics, especially in piping and hydraulics. Then there's force, which is perhaps one of the most fundamental quantities. We measure force in newtons, symbolized as N. Recall that 1 newton equals 1 kilogram meter per second squared, or kgm/s2. Power is next, representing the rate at which work is done or energy is transferred. Its unit is the watt, W, which is equivalent to kgm2 per second cubed. Power helps us quantify how quickly work is being performed. Pressure is another critical quantity, measured in pascals, symbolized as P1 pascal equals 1 kilogram per meter per second squared. It describes the force exerted per unit area, which is vital in fields like hydraulics and aerodynamics. Then we have charge, measured in coulombs. With the symbol C, a coulomb represents a specific amount of electric charge, and understanding this is key in electrical engineering. Moving forward, capacity, measured in farads, F, indicates a device's ability to store charge. The unit is expressed as CV, where C is charge and V is voltage. Resistance follows, measured in ohms, omega. It indicates how much a material opposes the flow of electric current, and its reciprocal is conductance. Next is inductance, measured in henries. H, it quantifies a circuit's tendency to oppose changes in current, with the symbol WB, where WB stands for Weber and A for ampere. Finally, we have energy and work, measured in joules. J1 joule equals a Newton meter, or Nm, and can also be expressed as kgm2 per second squared. This is the fundamental unit that links all these quantities in physics. By understanding these derived quantities and their units, we can analyze physical systems more comprehensively and accurately. They form the backbone of many calculations in engineering and physics, connecting fundamental concepts to real-world applications.